The codes are conservative. Why add conservatism to conservatism? So be brave. That's one message to the industry. And also try things out that no one has done before.
Kia ora, I'm Troy, HERA CEO, and welcome to Stirring the Pot. Thanks for connecting. If you're new, here's what you can expect. We're going to be talking the tough stuff, the things that keep us metalheads up at night. There are many challenges facing our industry and equally many opinions on how we should tackle them. Stirring the Pot provides a facilitated forum to discuss and challenge these viewpoints.
So let's get to the nuts and bolts of it. Today we're talking with Phil Gaby, who is Project Director at Holmes ANZ and a civil structures designer with expertise in bridges, wharves and water retaining structures. Specialising in design and constructing projects and alternative designs where value engineering is needed to bring projects back on track, Phil's passion is delivering efficient, elegant, quick and easy to construct affordable structures with the lowest practical environmental footprint. Join us as he chats with our structural sustainability engineer, Dr. Amir Shah Mohammadi, about structural steel design for bridges in particular and how we can push the boundaries of these designs to be more innovative and courageous.
Steel bridges, with their durability, strength, and remarkable engineering, have played a pivotal role in connecting communities and fostering economic growth. Steel bridges not only provide functional benefits, but their elegant designs also enhance the visual landscape and becoming iconic landmarks. Kia ora everyone, I'm Amir Shah Mohammadi, Senior Engineer and Researcher at Heavy Engineering Research Association. Today, we get on an attractive exploration of steel bridge design by inviting Mr. Phil Gaby, Project Director at Holmes, Australia and New Zealand, whose wealth of expertise in this field is truly remarkable. Very welcome, Phil. If there is anything you would like to add to my introduction, please feel free.
Just to say hi to everyone, and thank you, Amir, for your lovely introduction.
Thanks, Phil. So let's move on to the questions now. Could you please start by telling us a bit about your career and how you get into steel bridge design?
Oh, yeah, sure. I actually started off as a buildings engineer in a small consultancy in Otahuhu, and we did everything from sewage treatment plants to industrial buildings. And from there, I moved on to work for Fletcher's for a while on high-rise construction. Then I ended up spending 2 years in Bangladesh building stuff for the American government, and then moved on to the UK for 10 years. When I arrived in the UK, there were no jobs for building engineers, but there were a few for bridge engineers. So I had reinvented myself when I arrived in the UK and spent 10 years inspecting, assessing and strengthening bridges. Very few new bridges, but I learned a lot about bridge analysis through the assessment program. Moving back to New Zealand, I joined Becker, and while at Becker, I did quite a few interesting designs in bridging, more new bridges this time rather than old bridges. They included things like balanced cantilever concrete boxes and push bridges, also concrete boxes. 2006, I moved to Holmes, and at the similar time, Ray from HERA did a talk on steel bridges, and it captured my imagination. So HERA are to blame for my entry into steel bridges. Since then, I have done plenty of steel bridges, and so that's how it all happened. Blame Ray, my good friend.
Awesome. Thank you so much. That's really great to hear. Now, can I ask you to share a few examples of steel bridges you have conceived and designed in New Zealand and Australia? And if you have any slides, feel free to share.
Well, can I actually start with a couple of bridges that weren't steel bridges and how they kind of actually fit in nicely with the theme, because you can see evolution of themes here. So here we go. Can you see this?
Yes.
And let's see if it'll do a presentation.
Yeah.
There we go. I'll just go
Awesome.
back to the beginning. Well, when I was in that buildings firm in Otahuhu, this is my first bridge, which is a pedestrian footbridge made out of timber, and it's fallen apart. Timber does not last in the open air. It is being replaced now with a steel network arch.
Mhm.
And Becca are designing it, and funnily enough, I was the peer reviewer of it. So whilst at Becca, we did a few big bridges like the Upper Harbour Crossing in concrete, the concrete box girder bridge. And in Fiji, we replaced a rotten steel bridge with an incrementally launched concrete bridge. And but moving on, the first, as I said before, Raid from HERA introduced me to the idea of ladder bridges. So that Matahora Gorge is one of the original girder bridges that we designed. I conceived it, but one of our very clever young engineers, Bruce Galloway, designed it. And to the right there is a network arch that Ray had also organised the great Norwegian chap who invented network arches to come out to New Zealand. So we decided to build one across the Waikato River. And Michael Chan, who now works at Opus or WSP, and Rob Preslin finished the design of that second structure. So I don't know if you've driven over the big arch. You probably have if you've gone to Taupo. Some other bridges recently that we've done. Our Auckland office designed the structure on the top left, sorry, and that was something we conceived with Emmett's, and it goes from the main road to a cemetery, which is of great value to the local iwi. To the right is something we do a lot of, and that's farm access bridges. I love farm access bridges. You learn so much about efficiency and working with nature rather than fighting against it. And down the bottom left is a bridge that we launched across the Waikato River a few years ago, and down the bottom, another farm bridge, which was an alternative to a modular design. It was 70% of the way to the modular design, hence the fact that we won that job. I'll just do a couple more. We often get involved in alternative designs because clients run over budget, and we generally can cut 20% out of the cost of a bridge by using some tools that I'll share with you later. But here's a big footbridge in Palmerston North. It started off being a box girder bridge, and I'll explain why you've got to try and avoid box girder bridges unless you absolutely have to use them. And it's not because they're bad, it is because the codes are very conservative for box girder bridges. And this is something we're building right now. It's a network arch plus truss side spans to carry the water main for Wellington and Porirua across the Hutt River, and they're providing a cycleway on the other side. Again, this is an alternative design using the ideas that I will talk about later. We managed to knock about $10 million off the cost of this bridge and brought the project back into budget. Okay, let's go back. How's that? That's some of the bridges that we've done. Now, most of these bridges, I mean, I'm generally involved at the front end of the job, but we have a whole team of fantastic designers who do the real work. So I would not claim to be the sole designer of any of these, just part of a team.
Amazing. That was really interesting. Thank you so much for sharing these experience and these examples. My next question is about network arch design. How did the network arch design compare to more traditional solutions in terms of its performance?
Oh, they're fantastic performers. They Oh, a 100-meter span network arch will, let's put it in a different way. Say 120-meter long traditional steel bridge will weigh about 300 tons of steel. A 100-meter network arch will be about 120 to 130 tons of structural steel. To 200, depends on how wide it is. They are so efficient, but they are more complex to fabricate. So there are situations where they are really good, and there are situations where a traditional steel or precast bridge will be cheaper.
Okay, thank you so much. That's really impressive. And I'm curious to know what has been the thinking behind the Perry Bridge, which features sloping arches instead of vertical arches.
Yeah, this is Perry Bridge, and this was an idea that I had fermenting for about 10 years, and we finally found a situation where we could use it. And so Tim Brook and I worked on the concept, and then Tim took it through to detailed design. He's one of our engineers. Now, the leaning arches, for this reason, the bridge is only 3 meters wide and it's 130 meters long in a single span. So if you had vertical arches, the deck would be wobbly. But if you slope the arches, they kind of self-brace the structure. They fall into each other. So it is much stiffer than a parallel arch system. And that is why, for this bridge, we went to sloped-in arches. And when we did the detailed and sophisticated analysis that we do, we found that, it performed really efficiently for this longer span, thin bridge. Also, the hangers are on different inclines as you go across the bridge, and that also braces everything. If they were vertical, things can swing sideways. If they're on a slope, then if the load goes one way or the other, some hangers tighten, some loosen, but the thing doesn't swing. So, yeah, for a very slender bridge, it is not particularly lively, which is great for a cycleway pedestrian bridge.
That's really the killer solution. I've got a question about the Matahora George Bridge. Why did you choose a ladder bridge for the deck, and what was the reasoning behind the sloping steel piers?
Yeah, the Matahora Gorge Bridge is a classic location for a steel bridge. It is very difficult access. The river below is 70 meters down from the bridge deck, and from kind of one side of the gully to the other is about 120 meters. So why a steel ladder bridge? Easy to erect. You do not need big pier caps. You just sit the girders directly on top of the columns. And constructing pier caps in that situation is very awkward. Now, why the sloping columns? Well, those columns are only about 25 meters long. And if we had vertical columns, they would be 60 or 70 meters long. They would be unaffordable. Also, the structure cooperates with nature. With sloping piers, you're actually stabilizing rather than destabilizing the slopes. So, yeah, they made really good sense. Now, it's a zone of high seismicity as well. So concrete and high seismicity are not a good combination. Steel bridges like this are 60 to 70% of the weight of a traditional concrete bridge. And so that's a whole lot less seismic demand that the substructure has to deal with. So there's a few reasons. Now, steel ladders, as opposed to multi-girder steel bridges, multi-girder steel bridges need pier caps, whereas a steel ladder does not need a pier cap. It can sit directly on the columns. That saves one of the more complex construction challenges that you get with bridges. And with the transoms now, with a steel ladder, it is in fact a ladder. They have what they call transoms that span between the main girders, which are spaced as far apart as possible. And on top of those transoms, you drop precast units and then pour a topping. Very easy construction, very modular construction. And the other nice thing about a ladder bridge over a multi-girder bridge is that because there's only two girders and they're spaced widely, the load share between the girders is very uniform, and therefore you use about 10% less weight of steel with a ladder compared to a multi-girder bridge.
I see.
So there's some reasons.
Thank you so much. Regarding the Bridge 20 on Transmission Gully, why did you choose a steel box structure rather than a concrete one in this particular situation?
Oh, look, that's obvious. That's obvious.
Yeah.
We should not be using concrete boxes in high seismic zones. They are many times heavier than steel bridges, and the foundations become massive. And so purely the idea of going steel composite rather than, say, a balanced cantilever here was to keep the weight down and therefore make the seismic demands manageable.
Okay.
And the other thing about this bridge is it's only about 230 metres long. You need a bridge of about 500 or 600 metres long if you want to go to a concrete box because of all the formwork costs and temporary works and things. So it isn't really long enough for concrete box type of structure in any case. Now, the disadvantage with the concrete box here, with the steel box, was that we needed to go to steel because we were launching the bridge and it was on a curve. And steel boxes are very good torsionally. So that meant that the launching performance would be good. And that is not because steel boxes don't work well, it's just because the codes are very conservative when it comes to steel boxes. We could have done an I-girder bridge here if we'd lifted it up from the floor below.
Interesting. Now I've got a more general question. And in which situations do steel bridges particularly excel or demonstrate their advantages?
Oh, there's a bunch of them. Now, just going between the war between steel and concrete, there is no war between the two of them. We should be using the right materials in the right location. That's what I always think. Most of my life is in design and construct and alternative design. So the designs have to be competitive, which really helps you hone in on what the right solution is for the right situation. But when I come into a high seismic zone, I would not even consider these days going to concrete for the bigger bridges. Big weight equals big seismic demands equals big substructures. In remote areas, miles out of town, where you have to cut materials, steel bridges come into their own. They're lightweight. You can put the whole bridge on the back of a truck and get it there almost in one piece, and then you can throw it up in next to no time and drive away. A concrete bridge in that situation takes a lot longer to build. And quite often when you're in remote situations, there's weight limits on roads and bridges, which means you're limited with the size of concrete girder you can carry. So remote areas, we do so many bridges in remote areas for local councils and farmers, and we generally find they're steel. The longer spans suit steel, like anything between 60 and 100 metres. If someone comes up with a concrete bridge, let me come up with a steel bridge and then we'll compare notes. Now, with a bridge, you don't just look at the bridge deck, which is what some people do. You have to look at the substructure with the bridge deck. Quite often a concrete deck will be similar cost to a steel deck or even cheaper. But when you add in the substructure, that's where reality hits. So longer span bridges, we're doing bridges, single span bridges up to 130 metres in steel, and they're just wasting everything else in terms of cost, much cheaper. Now, the great thing about steel is you can reuse it. We regularly put refurbished railway spans, steel railway spans, back on top of new piers. They're lifted off, taken away, fixed up, and brought back to site. Or they're taken away and used on another job. So Kiwi Rail uses this process of reuse all the time. They've got yards of these steel spans that they refurbish and reuse. So off comes a badly damaged span, on goes a new one. They take the badly damaged one away, repair it, and then put it back somewhere else. You cannot do that generally with, say, precast concrete. And the other really cool thing about steel is you can use modular construction. And Eastbridge, who we work with a lot, regularly build modular bridges in Papua New Guinea and Fiji, all over the South Pacific and in New Zealand. And they're pretty similar. They're set up to punch holes and angles and bolt them together. Very quick to design, very easy to erect in small pieces. You can fit everything into a container and away you go. So they're the places. High seismic zones, remote areas where you need longer spans, you can reuse them, and modular construction is really suited to steel.
You brought excellent points, particularly about the modular design and reusability of steel bridges. Now I'm going to ask a challenging question. If you had the opportunity to make changes to the existing codes or regulations, what modification would you propose to further enhance the economic viability of steel bridges?
Look, what changes to the code? Well, I'd move away from Ostroids. That won't be very popular. Or some clauses in particular. There are some really draconian clauses within the composite design section on how much reinforcement you need in the slabs that go over the top of the beams. It's about 3 or 4 times what was traditionally used at the Ministry of Works time, and it's mandatory. So what we're doing these days is throwing all this reinforcement into the slab of these steel bridges, and that costs a lot of money. I mean, there are hundreds of tons of steel, I believe, are wasted a year in the form of reinforcing. Now, reinforcing costs somewhere between $3,000 or $3,500 or even $4,000 a ton to supply and fix. And if you have a 100-ton of structural steel and you've got 50-ton of reinforcing steel because of the requirements of AS 5400, you'd have to ask yourself, does this make sense? Now, I don't think it does, because I have looked at literally tens, if not hundreds, of steel bridges in New Zealand and in the UK, where I worked in assessment, which have almost no reinforcement in them and have done just fine. So there's one thing we could do. We could look critically at some of the clauses in the bridge manual, which refers us to Ostroids, and see whether they are really relevant, and don't get frightened to actually say, nah, that doesn't make sense in the context of New Zealand. So that's one. The other thing I would do to our codes is invent a better way of designing box girder bridges. They're a really good system, but they are penalised by our codes. And I think it's because a few of them fell down in their infancy, and identical to the Auckland Harbour Bridge type box girders, there were problems with the procedures they were using. Out of that come the BS 5400 methodology for box girders, and it's with us today, and it never ceases to amaze me. We regularly end up with 20% more steel with our box girder bridges compared to eye girders. It should be the other way around. Or at least similar.
Brilliant feedback. personal question. Among your various steel bridge designs, which one holds a special place in your heart and why?
You would be surprised. I'll just get it up, and
Ah,
here we are. Window, presentation. This one.
ah,
It's a little bridge. It's a 40-metre single span bridge located out at Bering Head in Wellington. It's a very remote location. Why do I like it? Well, it's materials efficient. Why is it materials efficient? It works with nature and doesn't fight against it. How could that be? Well, the conforming design that we competed against had normal standalone abutments that acted like retaining walls. And the abutments had about 8 piles each to hold them up because of the seismicity in the region. So we just said, well, why don't we let one riverbank hold the other one up? So we made a fully integral, fully framed up steel structure. And we went from 8 piles to 3 on each abutment. We also got rid of 70% of the abutment concrete because of this much more efficient system. And what's more, because it's completely framed up, a fully integral steel bridge, it is a whole lot less lively than a non-integral bridge. The framing and the interaction with the soil dampens the vibration on integral bridges by a factor of about 5 in some cases. Also, by framing it up, we reduced the bending moment at midspan, and we greatly reduced the weight of structural steel in the bridge. So, working with nature led to a materials-efficient design. And actually, it looks pretty good. Nice, slender ribbon bridge.
yeah.
And it was quick and easy to build. The whole thing was designed around constructability. And you guessed it, it was about 30% cheaper than the conforming solution because, again, it was materials efficient, it worked with nature rather than fought against it, and it was quick and easy to build. So I love this bridge, and we do these sort of bridges all the time, all over the country. Regularly, we end up getting rid of super T or hollow core bridges in remote areas and doing this sort of structure, which is really good because those remote areas, people can't afford gold-plated solutions. And of course, lightweight means great performance in high seismic regions, and we have lots of those in New Zealand.
Awesome, yeah. It was like a metaphoric answer for me. I was expecting that you're showing one of your massive iconic bridges, but we can see that there are a lot of big stories behind smaller projects. So it was really interesting.
Yeah, well, with the smaller projects, there's a lot more smaller bridges being built. And I am shocked at some of the designs I see. They are so chunky. They do not need to be. And I'd love to think that we would start to be a little bit more environmentally friendly by cutting material volumes down. And at the same time, having things that are easier to build and look elegant and all those other wonderful things, and they're affordable, of course. Yeah.
Amazing. Big lesson for me. Thank you for sharing your insights. So let's go to the last question. Can I ask what message do you have for the bridge industry to take on today?
Yeah. I would say learn to manage your fear. Many designers get the number from the analysis and add 20%. But go away and work out how many trucks you need to put on a bridge to reach its ultimate limit state capacity. You might remember the Mangamahu Bridge that we talked about earlier, the network arch, or did we not talk about that? I don't think we did. We didn't talk much about it. It's an 85-metre span network arch. I worked out that you needed to put 3 you needed to stack 40-ton lorries head to toe across the bridge and then put another layer of them on top and a third layer on top of that, plus 2 more lorries on top of that to get to the ultimate limit state capacity of the bridge. There is... So, the codes are conservative. Why add conservatism to conservatism? So be brave. That's one message to the industry. And also try things out that no one has done before. Now, we made mistakes on our first few ladder bridges and network arches, and they still make me a little nervous, some of those mistakes today. They've all been checked out and fine, but I wouldn't do it the same now. You will always make the odd mistake when you try something new out, but there's no progress without innovation and trying stuff out. If we hadn't have taken the risk and not listened to Raed, we would just be a normal run-of-the-mill bridge design team that doesn't know how to handle steel properly. So the benefits have well and truly outweighed the risks associated with trying something new. Another message for the industry is I would think about this, folks. Focus on getting the concept right rather than trying simply to satisfy code clauses. The codes have become so complex that people spend their time trying to satisfy the code. And to a certain extent, we've dropped the idea of creative thinking around concepts. We need to regain that, recover that. Perhaps we need to simplify the code so we don't have to worry about working out what the clauses mean, so that we can focus on what I call real design. Getting the idea right, using the right solution in the right place at the right time for the right purpose. Now, I've got one more message. Am I allowed to?
Of course.
Drop that in?
Of course.
Learn to work with nature rather than fight against it. Matahora Gorge is a bridge that propped itself off the cliff faces because they were there, they were rock, but it did it in a way that didn't destabilize the cliff faces. It helped to stabilize them. So, and in using nature that way for this bridge, we won the job. So simply because of the way we did the piers, we cooperated with nature. Secondly, push hard to be materials efficient. Now, I have to be materials efficient. One, I'm an environmentalist, but secondly, also I love winning. And if I am materials efficient, then I can win the D&C work. One of the contractors I work with, and we've done about 40 jobs together, we have an 85% success rate because we go for materials efficient designs. It's pretty good. So, yeah. And the next thing is, if you do those two things, if you cooperate with nature and you go for materials efficiency, you'll end up with elegant, affordable, durable, and resilient structures 9 times out of 10. There you go.
Brilliant messages. Personally, I learned a lot from them. Thank you so much, Phil.
Pleasure.
And thank you for sharing your experiences in the field of steel bridge design. It has been really an enlightening conversation, honestly, and we appreciate your time and expertise. And at the end of the conversation, I would like to thank everyone for watching this interview, and I hope you enjoyed.
So there you go. Thanks for joining our conversation with Phil today. If you'd like to connect with him, you'll find his details in the show notes. This was a great interview which challenges us to be more courageous with our designs by accepting a bit of risk on the understanding that without trying new things out, there is no progress. Food for thought until we see you next time. So hit subscribe, and if you liked what you heard today, please like, review or share with any metal minds you know. Let's spread the word. If you like what you heard, you may be interested to find out more about our structural systems team and the research and work they're undertaking to support steel bridge design. You can find more in the show notes.